Alright. So, we've been reviewing supersymmetry in 4 dimensions, and we'll continue doing that in this lecture. And it looks like also in the next lecture, because there's really no point writing down the MSSM without knowing how to write down supersymmetric gauge theories, both abelian and non-abelian. And both take a bit of time and work. So today I'll do the abelian case. And if I go at the planned speed, then by the end of the lecture I can write down for you the Lagrangian of supersymmetric QED. And obviously if we can write supersymmetric QED and then in the next lecture supersymmetric QCD and supersymmetric chiral gauge theory with left-handed doublets, then basically we've got a supersymmetric standard model, and then we have to fix up all the details. So that will be the strategy. Before I actually start with what I wanted to do today, there was a certain confusion in something I wrote last time. I'll try to clear it up just now. The supersymmetric transformation of a chiral superfield was written by me as this. Which is correct. And let's remember that Q is minus I del theta plus I sigma mu. This is DGR conventions. Wess and Bagger's conventions are slightly different. They drop this minus I as well as this I. So whatever it is, it's the same formula for variation of phi. The important thing though is to realize, okay, Q diagonal is similar to this. Important thing is to realize is that if I put in this up there, these i's cancel, and I have an expression which is delta phi is equal to del by del theta of phi plus other terms. Okay. That means that if I complex conjugate phi, then I get delta of phi diagonal is exactly the same operator, not with a minus sign, phi diagonal. Okay. Last time I might have written it with a minus sign, if so that was wrong. This is with the same sign. And in fact, from these two we can see that just about any superfield will have, even if it's a real superfield, which is the case we'll discuss today, has this variation with the I present. So actually every superfield, we've used the notation F for the most general case, transforms like this, and this then can be used for the proof I gave that any integral of a superfield is a supersymmetric invariant. I gave that proof last time. So the proof of supersymmetry invariance is, to repeat it briefly, it's in 2 parts. Any product of superfields is again a superfield. That's obvious because we started by defining superfields saying that they are an expansion in theta and theta dagger. If we don't put any constraints on them, of course, some function of x theta and theta dagger, if I multiply with another function of the same variables, the result can only be a function of the same variables. Okay, but more particularly, any superfield transforms this way. This we've already said. Okay. And this is compatible with the first one because if the given superfields transform in this way, then the product of them also will transform in this way. Because this is a first order infinitesimal, is a differential operator of first order, so it distributes on all the factors. Okay, and then we have the fact that the last f or d component transforms as a total derivative, which I showed last time. under supersymmetry as a total derivative. That completes the proof that any integral of a superspace action, where that action will be integrated in only theta if it's a chiral superfield at the end, or theta and theta dagger if it's a vector superfield. Those integrals pull out the corresponding last terms, and those all transform as total derivatives. Okay, so that's the review of last time. Now this time, we want to consider a different constraint, which is different from the chiral constraint, and in some sense is the only other constraint we can think of, and that's the constraint which defines vector superfield. So, impose reality of the whole superfield. So, a general superfield F, we set it equal to its dagger, and we call the result V of x, theta, and theta dagger, and it's called a vector superfield. Okay. Now, last time or some time before, I had written down the expansion of a general F, any arbitrary superfield, okay, all the way up to the theta to the fourth terms. And now the expansion of V is exactly the same, except that all the coefficients are constrained to be real. Nothing more than that. But we need to do this because we need the notation. And here you will see that in supersymmetry, we often run out of letters to use. But let's try to write this. So the first component of a vector superfield V I'll take to be a scalar, ordinary scalar field, but it will be real. This is unlike how a chiral superfield worked, where the chiral superfield was necessarily complex, therefore its first component was complex. Okay. Now this has theta psi. This is not real, but we can add to it its conjugate. That's real. Okay. Next, in order theta theta, we'll call the coefficient m, and then we just add to it its conjugate, theta dagger, m star. So m is a complex scalar field, but it occurs in both places, so thereby satisfying the reality constraint. The next term is theta sigma mu theta dagger times a mu of x, and it's easy to see that this combination is real. Therefore, the coefficient is also real, and we see that we've got a vector field which is real, which is very important because vector fields are always real. So this looks promising. We've probably got something useful. Then in the order of 3 theta, we have this plus its complex conjugate. So repeatedly we see the usefulness of two-component notation. This is the contraction between these two, this contraction between these two, and then these are the complex conjugates fitting at nicely. And finally the last term is chosen with a conventional factor of half, theta squared, theta dagger squared, d of x. These are all of x, of course. I haven't bothered to write that everywhere. And d is real. Okay. So I hope it's completely clear what is the field content of this vector superfield. Not all the fields appearing are real in a natural way. This is naturally complex but occurs with its complex conjugate. Same is true of lambda, because lambda is a fermion, so it has no choice to be real. So it will occur with its complex conjugate, so is psi, and then d is real and c is real. Any question? Yeah, that's correct. Thank you. So the key point is all the constraints that we are allowed to impose have to be preserved by supersymmetry, otherwise it's useless. They'll just be true once, and then when we make a super transformation they'll fail. But it does actually commute with supersymmetry. And that's easy to see when you realize that the supersymmetry transformation shifts x mu by a real amount. It's a transformation in superspace. It shifts x mu by a real amount and theta dagger by complex conjugate amounts of each other. Okay. And then if you impose reality, you will see that such a transformation doesn't make the field complex. However, imposing reality does not commute with imposing chirality. That is, if I put d dagger on the field to be 0, which is a chiral superfield, then I can't impose reality. Okay, that's obvious. I've even shown it before. Because if something is chiral, if a superfield is chiral, then its dagger is anti-chiral. That's the proof that that constraint doesn't come into play. Okay. Now, actually, although I've just introduced vector superfields, we've actually seen them implicitly without recognizing them for what they are, because recall that if phi is chiral, then we used the quantity phi, dagger phi. This is clearly real, it's also not chiral, and so it is an example of a vector superfield. Here again we see this interplay. The way I wrote this, it was implicit that I was talking of a fundamental field. Okay, here is not a fundamental field because phi is a fundamental field, so phi dagger phi is a composite field. Okay, but in supersymmetry and actually in all of field theory, at least at the classical level, what is fundamental, what's composite, what's so composite that it's a term in the Lagrangian or a potential term, these are all fields. Okay, when we do quantization, we need to know which one we are integrating over and how the functional integral is defined. But for symmetry purposes, fields are just fields. And in fact, in that sense, the parameter lambda of gauge transformations, when a mu goes to a mu plus b mu lambda, we call it a local gauge symmetry. That means lambda is a field as well. Okay, it's a parameter which is a field. So here's an example of a vector superfield, which is actually a term in the Lagrangian. And here's another example. I just take this and add it to this. This is also a vector superfield. It's another way of making something real. Okay. This one we've used. We saw that it's a kinetic term. This one we haven't used yet, but we are going to understand what use it is. For that, let me write phi. And we've seen the expansion of chiral superfields repeatedly, but now I'm going to write its components with slightly different names, anticipating the fact that this field I'll be using not as a fundamental field of the theory, but as a parameter. Okay, I'll explain what use it is, but first I'll just write it out. The expansion itself is familiar to you. I'm just going to call the first component alpha. Then these are the components which arise from expanding y about x. And then there are these fermionic components. F I'll keep calling it. I've just changed the name of the scalar and spinner from phi and psi to alpha and chi. And phi dagger can be written similarly. Now once I've done that, what is phi plus phi dagger? I just have to write out phi dagger, which I'm not going to do here, and then add it with phi. So alpha occurs in phi. In phi dagger we'll have alpha star. So in the sum we'll have twice real part of alpha as the first term. Okay. So this is going to be an example of a vector superfield. So its first term should be real, and it's going to be similar to C. It's going to be twice real alpha. Then we'll have root 2 theta chi plus Cc. I'll be a little where there is no possibility of confusion. I won't write down anything in gory detail. Now here's an important term, twice theta sigma mu theta dagger del mu of im alpha. Alright, because we take this term which has an I, In phi dagger, the same term occurs with the opposite sign because that's the I, and therefore instead of getting alpha, real part of alpha, we end up with the imaginary part of alpha. Then we continue writing this, which is sort of tedious, minus I by root 2 theta dagger sigma bar mu del mu chi plus Cc. And finally, the last or D term of this superfield, and we see that it actually is box of real of alpha. So what do we get when we look at phi plus phi dagger? We see that out of the three components in a chiral superfield, alpha, chi and f, the three independent fields contained in there, the real part of alpha occurs at the beginning and end. The imaginary part of alpha occurs somewhere in the middle, and then chi occurs also in first and third order in theta, and f occurs in the middle. So this is phi plus phi dagger. But I haven't told you why I've written phi plus phi dagger at all. And the reason I've done that is that it's a vector superfield, but it contains the independent degrees of freedom of a chiral superfield, which are less in number. And so I can consider the transformation, a very simple field transformation, where I take an arbitrary vector superfield and I shift it by this phi plus phi dagger. What we are going to see is that this shift will be the equivalent of gauge invariance, of a gauge transformation on V. Why do I say that? Well, we saw that in its long expansion, V contains a gauge field mu. And we've just seen that in the expansion of phi plus phi dagger, we have an object del mu of some parameter. That means if I add this thing to V, the result will shift mu by del mu of some parameter, and that's a U1 gauge transformation. Okay. However, it will also do lots of other things to all the other components. So we see that gauge transformations cannot just be made on one field in a supersymmetric theory. They must be made on the whole supermultiplier. So if V is the superfield containing a gauge field, then the whole of V must shift consistent with its properties as a superfield. And you see that this is more or less the only choice, because V was a superfield that had no Lorentz indices and it was real, and phi plus phi dagger is a superfield that has no Lorentz indices and is real. There isn't anything else you can think of. Okay, so now yes, any question?
I mean, you can have an equivalent combination I of phi minus phi dagger.
You can. It's the same exactly. There's no difference. I can. That's obtained by just renaming phi as I lambda or I something else, and I'll be doing that. It's just the same. Okay. So now I can ask the question: what does this do to all the different fields contained in V? So let's list the fields that were in V. There was a C, there was a psi, you can look at your notes. There was an M, an mu, a lambda, and a D. It's very, very annoying in the beginning to have so many symbols. Yes. Yes.
What are we doing if V goes to V plus?
What are we trying to achieve by sending V to V plus phi dagger? I have noticed that V contains a gauge field in it, mu, and I've noticed that phi plus phi dagger for a very general phi contains del mu of some scalar field in it in the same place. Okay, same place being the place where theta sigma mu theta dagger occurs. Okay, so I'm motivated to guess that phi plus phi dagger looks like a gauge shift in the gauge field, a U1 transformation of the gauge field, and therefore I am going to propose that V plus phi dagger is a gauge transformation on the full superfield V. Okay, and I see that when I define a gauge transformation in a supersymmetric theory, supersymmetry must be preserved while I am making my gauge transformation, which means I couldn't have just said, well, V has a gauge field mu and mu goes to mu plus B mu alpha. That's just not okay, because I'm never allowed to add just a scalar function to or some function to another function. I have to add a superfield to a superfield. So I have to elevate gauge invariance to a principle where the superfield V shifts in a correct way, And I'm just going to argue that actually B has to shift by an arbitrary phi plus phi dagger, which contains an arbitrary im alpha, which is the arbitrary gauge parameter shifting A. But we have to accept that a lot of other fields in B will all be shifted, and we'll soon see what that means and what to do about it. And here we are already sort of embarking on the territory which will lead to MSSM, because what's the point of the minimal supersymmetric standard model? It has to be a gauge theory, because that's what the standard model is, and it has to be supersymmetric. Okay, but these two things are not easy to combine with each other, and today we are seeing how they are combined. Okay, now we just have to write things out in components. So remember for yourselves that this is the first term, this is the order theta squared, another order theta squared, theta cubed, and theta fourth term in the expansion of B. And I've claimed that there are no other terms. As usual, you can amuse yourself by counting up bosonic and fermionic degrees of freedom. If you count off shell, you will get 4 plus 4 plus 4, 8 fermionic, 1 plus 2 plus 4 plus 1, 8 bosonic. So what we find is that this shifts C by twice real alpha, it shifts psi by chi, it shifts M by F, it shifts A mu by minus twice del mu of M alpha, it shifts lambda by lambda minus I by 2, sigma mu del mu chi dagger, and it shifts D by minus box del alpha. So we have to somehow accept that gauge transformations, that this transformation of B, if interpreted as a gauge transformation, does exactly the thing we want on the gauge field, but it does lots of other stuff, and we have to understand what that other stuff is telling us. So here are a couple of observations which you can see in front of your eyes. The first three lines of this are telling us that we can remove these fields. C, psi and M can be removed by an opportune choice of real alpha, chi and F. They're just shifts in the field. A gauge symmetry involving a shift in a field means you can just choose the gauge parameter to be minus the original field and go to a gauge where that field is 0. I hope you know that you can't do that when A mu goes to A mu plus D mu lambda, because the generic A mu cannot be written as D mu lambda. That's the whole point. When it can be, you can gauge it away. So the first observation is we can gauge away, which means set to 0. C, psi and M. The second observation is that defining a real function beta of x, I won't call it lambda because there's a fermion called lambda.
When you said that you cannot gauge away mu, means simultaneously at the same time with.
No, you cannot gauge away a general mu by adding d mu of something. If you could, then all gauge fields would be gauge equivalent to 0. If this worries you, please consider the fact that f mu nu is the curl of A, and if A mu was d mu of something, then f mu nu for that would be 0. So you can gauge away A.
C or
What?
What can you do with the other one?
Because you choose alpha to be minus C.
Okay, there's a derivative there.
Yeah.
So you might want to solve imaginary alpha by saying that it's a path integral of A mu. So it's A mu dx here from some reference point to x. But then you have to depend on the paths. No, generically it will depend on the paths when the curl of A is A. So therefore you can't invert the A mu of it.
Another way to say it is to realize that A mu contains 4 independent functions. I surely can't choose one function alpha such that del mu of it is 4 independent functions. Okay? C contains one independent function and I have one independent freedom here. Likewise, psi is a spinor function, I have that much here. And M is a complex scalar, but I have that much available here. So I can do this. However, you will have noticed that while I can gauge them to 0, the next time I make a supersymmetry transformation, they'll come back. Okay? Why? Because any specific choice of components of a superfield breaks supersymmetric invariance. Okay, it's not covariant to choose that. It's like saying that I can perhaps gauge away the three component of A mu, A3 let's say, but the next time I make a Lorentz transformation it will come back. Okay, so if you want to visualize what we have to do when we work with this system, every time we make a supersymmetry transformation, we have to go back and impose a gauge in which these guys are zero. We don't have to, but we would like to. Could help us. Okay, this goes by a name. This choice is called Wess Zumino gauge, and it's certainly the gauge in which the physics is most transparent, because what it's already telling us is that these are not any physical degrees of freedom of the vector superfield. The very fact that they can be gauged away tells us that. The fact that this one undergoes gauge transformations tells us that it's a U1 gauge field. The only Lagrangian you can write compatible with such an invariance is going to describe a U1 gauge field. And if we are lucky, its Lagrangian will be minus a quarter F mu plus other things. So we have to strive to find such a Lagrangian. This one is a fermion, and this one is an auxiliary field. And we can, the second, okay, so let me first finish saying this. Defining beta x equals minus 2 im alpha. Alpha was complex, beta is real. We have the gauge transformation. And this, I've already said this. Just writing it. So A is a U1 gauge field. So that brings us to these two. And a very nice fact is that we can actually redefine them such that they are invariant under the gauge transformation. And that's done as follows. Remember that in the superfield expansion, I chose the cubic term in theta to be multiplied by lambda. Whatever multiplied that, I called it lambda. But it wouldn't have hurt me to call it lambda plus some sigma mu del mu on psi. Psi is another field in the expansion of that superfield. So, in the set of fields which occur in the expansion of that superfield, I can redefine fields among those if I want. And so, the redefinition that is convenient is to send lambda to lambda plus I by root 2 sigma mu del mu outside adder, and d to d plus a half box of C. Please understand very clearly that I am redefining these fields in terms of other fields which occur in the vector superfield. I am not redefining them in terms of other parameters. These are not other parameters. These are also fields which occur in the original vector superfield. Okay? With this redefinition, the vector superfield. Yes.
The point of view, I guess, is that you begin with the 6 fields.
Yes.
Then you make a redefinition so that lambda and d get redefined.
Precisely.
And then you put c and psi and m.
That's right. So actually, I could have listed. Thank you. So what Gautam is saying is that, and in fact, what I was just going to say as well, is that with this redefinition, we would have the same expansion as before, except by the time we reach theta dagger, then the coefficient is lambda dagger minus I by root 2 sigma bar del mu psi plus Cc. And then when I
lambda prime and then say that given you lambda will satisfy lambda prime.
Exactly. That's exactly what I mean. You can call it lambda prime. But what I'll do instead is I'll just say that instead of that naive expansion of B that we wrote before, which is valid, we'll write another one which is equally valid and related to that previous one by linear redefinition of all the fields. And the linear redefinition for the last term tells me that now the last term coefficient is written as d minus half box C. And now what happens is that when C shifts by a constant and d shifts by this amount, the two effects cancel each other. Although I'm afraid that it's not looking like they do now. D plus half box C is inverse, so this should have been plus, and and this I think should also have been plus, check, because lambda plus sigma mu del mu chi dagger psi dagger, yeah, both are plus. Yeah, so that's exactly what I mean by my redefinition. And with this, we see that whatever gauge transformation you do by adding phi plus phi dagger to V, we see that lambda and D are gauge invariant. Instead of this, so in the new variables, after I go to the Zumino gauge, by setting the first three things to 0, I am left with an mu that transforms this way and a lambda that doesn't transform and a D that doesn't transform. That looks pretty good. Already we can see what's going on, because in the first lecture on supersymmetry I showed you a Lagrangian which involved a gauge field and a single fermion, okay, a neutral fermion, and so we can identify this lambda with that lambda which was there in that Lagrangian, and D being the last component, we can hope that it's an auxiliary field. So this is how the vector multiplet degrees of freedom come out. So unlike a chiral multiplet where the scalar and fermion and auxiliary field were all the content of that, here besides this content which we need, there's another set of fields which needed to be gauged away. That's the only difference.
So is it like even for a vector superfield, when we impose your supersymmetric gauge transformation, all it does is only shifts the U1 field by S.
Yeah. So now actually no. So thank you. That's exactly the comment I was going to make now. So to summarize where we have reached, we have gone to Zumino gauge. Okay. Now the parameter phi plus phi dagger depends on, let's list all the independent fields it depends on. I don't want to rewrite the expansion of it, just list all the parameters it contains. It contains real alpha, which is one independent parameter, and it contains im alpha, which is the second one, and then it contains chi and f, and their conjugates, and nothing else. Good. And now we see what's going to happen. We've used the real part of alpha and chi and f to fix the Zumino gauge. Okay, but this is an independent parameter. So if we choose a superfield phi plus phi dagger which only has im alpha and everything else is 0, then adding that to V will only perform this gauge transformation and nothing else. Okay, so we can perform U1 gauge transformations on V in Zumino gauge using a phi plus phi dagger with real part of alpha as well as chi as well as f equal to 0. So if you want to think of it sequentially, first we use a phi plus phi dagger with only these three parameters, and that doesn't transform the gauge field, but it sets the other fields to 0, whatever can be set to 0 in Zumino gauge. And then you can perform it with phi plus phi dagger with only imaginary alpha, depending only on imaginary alpha. And that gauge transforms the gauge field and does nothing else to any other field. All these statements are non-supersymmetric covariant. All these statements will change when I make a supersymmetric transformation, but once I have fixed a Zumino gauge, or rather once I have fixed a particular field content, then in that supersymmetry frame, if you like, these statements are true. Okay. Another way of seeing why this is not a supersymmetric covariant statement is that choosing phi plus phi dagger to have only an im alpha component and nothing else is not a supersymmetric choice. I fixed one ingredient of it. In fact, what does such a phi plus phi dagger look like? It has no first term. It only has the term, so in fact, that this is only minus 2 theta sigma mu theta dagger del mu in that. This is the choice of phi plus phi dagger, which means I just choose phi to be minus with the coefficient 1 theta sigma mu theta dagger del mu of something, some real parameter. Then phi dagger will be the same. Then I add them and I get twice that, and that's the transfer. That's the parameter which makes gauge transformations. However, if we want to make gauge transformations while maintaining supersymmetric covariance, then we should just say that it is V goes to V plus phi dagger for a general phi and phi dagger. Okay. In that case, we have to be prepared to live with the fact that all the other auxiliary fields which are gaugeable away, the C and psi and so on, will be there. We can sort of ignore them in the sense knowing that they are gauge artifacts, but they will be there. They are just as troubling or not troubling as the longitudinal component of the photon. It's a gauge artifact, but it's always there. Okay, and that completes this discussion. The last thing to be said here is that conventionally, we write this chiral superfield phi as I times capital lambda, where lambda is also a chiral superfield. Okay, so therefore the U1 gauge, so the summary of all I have said up to now, the U1 gauge transformation on a vector multiplier is V goes to V plus I lambda minus lambda. Okay, lambda will have the same expansion that I wrote for phi. The difference is lambda emphasizes the nature of this superfield, that it's a gauge parameter superfield and not a fundamental field. So we'll reserve phi from now on for fundamental chiral superfields. Good. Now I'd like to do a little exercise about canonical dimensions. We keep doing this from time to time. What's the canonical dimension we should associate to V? Okay. The way we associate canonical dimensions is to first figure out one component field in the superfield which we particularly like. That's a physical field, and that we know its canonical dimension, and then all the other canonical dimensions just follow. So V in any gauge has all sort of stuff, but then it has theta sigma mu theta dagger A mu. And then more stuff. So what does that tell me about the canonical dimension of V? This is enough to read off the canonical dimension of V. Come on. Surely it's the sum of the canonical dimension of A mu, theta and theta dagger. What are those? A mu is?
Mass dimension.
Mass dimension 1, thank you. That's what I'm looking for, mass dimension. And theta, we already identified its mass dimension. Half. How many people think the mass dimension of theta is half? Half or minus half? Who votes for half? Who votes for minus half? Wow, you have been reading your notes desperately last few days. I said this as unambiguously as possible, huh?
Half, so it should be minus half.
Thank you, minus half. If you expand a chiral superfield, it starts with a dimension 1 scalar, and the next thing is a dimension 3 half fermion. Okay?
If you express theta,
how did that work?
if you express theta sigma theta, so theta should have the same dimension.
Say that again?
In the Susi transformation,
Yes.
it goes to express theta sigma theta.
Excellent, thank you. That's one way to read it off.
Integral d theta theta is also. Integral d theta theta is what
That's
d
also.
theta has not.
Well, that is that way. The integral we used to read off the dimension of d theta, so that's not an independent starting point. Okay, very good. So everything points to the fact that the dimension of V is 0. Okay. Now notice that in the development of V in thetas, the next term after the gauge field occurs the next term here, this dot dot dot, is actually of the type theta, theta, theta dagger, lambda dagger, right? So with this assignment, the dimension of lambda dagger and lambda is 3/2. Then this is minus half, minus half, minus half. That's good because the fermion in 4 dimensions has dimension 3/2. And then the auxiliary field has, the B field has dimension 2. And we saw that dimension 2 is a good thing for an auxiliary field. It means that in the Lagrangian we get D square. Huh? Okay. So this is equivalent to dimension A mu equals 1, lambda is 3/2, D is 2. And we've seen this set of dimensions before. It's exactly the set of dimensions in the chiral superfield. But in that case, it was the first, second and third term, and in this case, it's like the third, fourth, fifth and sixth term of the superfield. Okay? That also tells us that the first 3 terms in this expansion, the ones which can be gauged away, all have somewhat unphysical dimensions. For example, the first term itself, the C, the field C, has canonical dimension 0. Okay. Now, we don't usually encounter fields of mass dimension 0 in 4-dimensional field theory, so it looks like it should be a gauge artifact, and it is. Okay. Moreover, lambda must have canonical dimension 0 also, which is correct, because lambda contains the gauge parameter im alpha, and del mu of that is what we add to A mu, therefore alpha itself should have dimension 0. So the canonical dimensions are fine, it's very simple, but it's a little surprising because here we've got a superfield which the whole thing has canonical dimension 0. We'll see that this has an interesting consequence in a few seconds. So what do we want to do next? We want to take this field of canonical dimension 0 and try to find the kinetic term. Okay, now we look for Lagrangians. We've sorted out everything we want to know about the field. Let's look for Lagrangians. So what's the kinetic term for V? There aren't so many choices. Okay, let's use all the assumptions available to us. There will be a d for x integral which I never write. Okay, but there will be an integral d2 theta and d2 theta dagger. We'll be allowed to drop one of these if the thing inside is chiral, but we know that V is not chiral. So generically things that we make out of V probably won't be chiral. So we should be prepared to integrate in theta and theta dagger. Okay. Now this whole thing has mass dimension . Very good. Okay, it has mass dimension 2, and that means I must find a Lagrangian of mass dimension. For counting of this, of course, I should count this. So this is -4 and this is +2, so it's altogether -2. So whatever I'm going to write here has to have mass dimension +2. How am I supposed to get a mass dimension +2 supersymmetry invariant term starting from a field V that has dimension 0? Del mu. Del mu is not supercovariant. Del mu does not commute with all of supersymmetry. Yes? D. So the thing to use, which anti-commutes with the supersymmetry generators, are the covariant derivatives D A and D dagger A dot, which we defined last time. So those will be our building blocks. Okay. So actually, I must say that del mu does commute with Q. Anyway, let's keep that aside for the moment. Let's assume for the moment that the building blocks are D A and D. Did I use strip D or capital D? I don't remember. This is what I used. Okay. So these are the building blocks. What are their dimensions?
Same as
d theta is correct. Okay, because this starts with d by d theta, which is the opposite of the dimension of theta, therefore it's +half. So how many of these together do we need? 4. Very good. So in superspace we seem to be heading for a 4 derivative term, and the simplest way to write one, and turns out to be quite correct, is that where I don't have to write any indices for you, because this D and this D are undotted spinners, so there's already an established convention. This index up, this index down. These are dotted spinners, so this index down, this index up. V itself is scalar, and the whole thing has dimension 2. And so this is my guess for a kinetic term. And I'm going to just argue, now I'm going to rub out D for x, and I'm going to put a numerical coefficient 1 by 8, which according to me is going to be the right normalization. How do we find out that this is right? Now we plug in V, the expansion of V in component fields, in the Wess-Zumino gauge. But actually it won't matter, because it will turn out this is gauge invariant. So even if we don't put the Wess-Zumino gauge, we'll get the same answer. Okay, that's an exercise for you. We just plug in V in component fields, and the answer comes out to be, with this chosen normalization, I get the answer a half T squared minus a quarter F mu nu plus I by 2 lambda sigma mu equal mu lambda. Okay, so this is good news indeed. We found an action for V which has the correct canonical dimension, which is super covariant. The only thing we didn't check was that it's covariant or it's invariant under the shift of V by I lambda minus lambda dagger, which is the superfield analog of a gauge transformation. Okay, so how do we check that? Of course, we've got the answer, and now we see that the answer is certainly gauge invariant, because these fields lambda and D are gauge invariant, F is gauge invariant, and the other fields, the nuisance fields C and whatever else they were called, M and so on, don't even appear. Okay, so this is gauge invariant, manifestly. But actually, it's easy to see that V goes to B plus I lambda minus lambda dagger is an invariance of the original superspace action. One easy way to see that is to realize that these things under the d theta and dx integrals obey the rules of integration by parts. Okay, all these d's, each of them individually obeys the rule of integration by parts, which means putting it here or putting it there up to an appropriate sign is the same thing. Okay, that means that this action can also be written as V times d dagger V. Okay. Now d dagger is particularly simple. It kills anything with a lambda plus lambda dagger, because there are two d's and two d daggers. So they are bound to kill anything which is chiral and anything which is anti-chiral. Requires a little work to see, because if it's d dagger, then the d daggers on the right will kill this, but the d's on the left, in order to kill this, have to come through the d daggers. They may give some residual terms, but an anti-commutator of d and d dagger is del mu, space derivative, so space-time derivative. So if you do everything properly, you will see that this shift is an invariance of that.
So is this same as d dagger? Can we write this as d dagger, d dagger?
Yes, but then you have to use put the indices. You can also do that. So let's do it once so that you get used to these manipulations. The only thing is, when I'm doing it online, I don't guarantee I get the signs right, but everything else is right. So I'll just say that d dagger, d, if I integrate over everything, is the same as V D dagger. B, again here the index contraction is undotted, undotted, dotted, dotted. Okay, but it's also the same as D, A, D, B dot dagger, B, D, A, D, B dot B. This is also true. As I said, I can't absolutely swear that there is not a minus sign somewhere, but it's otherwise the same. To achieve this, I would have to send one of these D's and one of these D daggers there. But since the two D's were contracted, they have to have the same index A, and since the D daggers were contracted, they have to have the same index B dot. And then you have to worry a little about which one is raised and which one is lowered, but these are all equivalent and all correct.
So this answers the question by, because this is the same thing as the del mu. We can find the anti-commutator and write as del mu B, del mu B.
That's the anti-commutator. What will you do with the rest of it?
Because it's symmetric.
No.
You can write
This is not the same as having the dA on the right side of this, and the difference is exactly del mu. So if you like, this term can be replaced by dA dB dot dagger anti-commutator half plus a half the commutator. This is very generally true, you'll agree. This is fantastically true. But now, this one gives me del mu, but this doesn't. This gives me something. So I don't think you will find it reduces entirely to del mu, but parts of it might. Yes.
We did something and finally we got to this answer for the band term.
Yes.
Now, let's say we didn't use the Zumino, we wrote down everything.
Yeah, we didn't. In fact, we didn't. What's happening here is that the terms the fields which are not. So the question was, did we get this after assuming the Zumino gauge? At first I said we did, but then later I retracted and said that we don't have to assume the Zumino gauge to get this answer. I'm only 90% sure of that statement. What I think will happen is, if you look at the first term of V, for example, you will get you will find that the C field which occurs, the first term of V is some real scalar C, will just drop out after DD acts on V and D dagger acts on V and then we integrate it. It just drops out. Okay. And one way to see that is, those are all fields which have a shift invariance, shift by an arbitrary function. On the other hand, we've just argued that this is gauge invariant. So that means in components also it will be gauge invariant, where the gauge transformation is defined as shifting those fields by an arbitrary function. Now it's not very easy to write a Lagrangian for a field which is invariant under shifting that field by an arbitrary function. You think of one. After all, if it was, then it couldn't depend on that field. Same statement. Understand what I'm saying? Okay, let me devise a hypothetical theory with one single scalar field phi, invariant under phi of x goes to phi of x plus alpha of x. Now write me any Lagrangian which is invariant under that. What? Tell me phi. How is it invariant under phi of x goes to phi of x plus alpha of x? Shift of a field by a function. You see, that function is the field. If I'm allowed, if I have an invariance when I shift a field by another field which is the same field, which is the same type of function, then obviously if the action depends on the field, it will depend on the shifted function. Therefore, it doesn't depend on the field if it has to be gauge invariant. What choice is there? I mean, there's a more specific way to prove what I'm saying, which is that you can do this calculation. The calculation is set out for you. You don't have to assume anything I'm telling you. Just plug in V in the most general form. Do this and you'll get an answer. I'm claiming this is the answer, but it may be wrong. But right away, my question is, what do you expect? Okay? It's just hard to see what you could possibly expect.
But if the C was like an X,
yes.
That
Yeah.
part of the feature, it would have. That's not the case here.
Actually, the reason it's not the case is that the gauge transformation depends on im alpha, while these three redundant fields in Wess Zumino gauge don't transform under im alpha, they transform under real part of alpha. So if you had a gauge field which transforms under real alpha and an axion which does the same, then you could have a gauge invariance.
So an independent matter field can be written down, which has just a shift thing, but not this.
But then with a gauge field, of course.
With a gauge field.
Yeah, but here the point is that only the shift of the matter field is an invariance. We've shown that. That was the nice thing about the way alpha, that parameter, broke up into its real and imaginary part. Only its real part affects the field C. It was also going to affect the last component D, but we redefined D so that it didn't act over there. It only acted on C. And its imaginary part only acts on A mu. So totally decoupled. So that transformation on that field alone and on nothing else should be an invariance of the action. So it's very hard to imagine getting gauge invariance. Okay. Now there's another, so these are among many ways of writing this. There's one more useful way. It's also equal to, this time I'll put back the coefficient correctly. So this is 1/8. This is minus 1/16. Integral d2 theta dagger of, this is a particular way of writing it, d dagger dA b times dA b plus its complex conjugate dd dA dot dagger b dA dot dagger. So what have I done? I've taken a somewhat asymmetric choice of putting 3 d's on one of the b's and 1 d on the other one. You can do that of course by partial integration. But the way I've done it, you see that I end up with a term that's not real, not manifestly real, may actually be real, but doesn't look real because this piece has 2 daggers and 1 undaggered, and this has only 1 undaggered thing. So I just add its complex conjugate. That accounts for the relative factor of 2 between this and this, and I claim the minus sign comes from one integration by parts, so I prove this. And this I am going to claim will be useful to us. So let me show you why I have done this. In order to do that, let me give a name to this piece, d dagger d on b. Okay, so I'm going to call that W. This W should not be confused with the W occurring in the superpotential. This W is defined to be minus a quarter d dagger dA on b, and therefore W dagger with b. Dotted index, sometimes people just call it W A dot. I'd much rather keep the dagger. Is again a minus a quarter to check the signs. dA dot dagger on b. So I've defined this. Okay, it's a strange beast because it's 3 different derivatives on 3. On the other hand, because of that, W has canonical dimension. Three-half, thank you. Okay, and we can write the action yet one more time. You'll see that we'll write this action many times. Now we can write it as a quarter integral d2 theta dagger W A dA b plus W dagger A dot d dagger dot b. That's pretty obvious.
Is this like the first order?
No, we'll see in this. Let me write one more line and you'll see what it is. It's not quite like first order. Anyway, this is true. I suppose you can see that because these three things on B make a W, and then there's a dB left, and the quarter has been eaten up by the definition of W, so you're left with just a quarter from outside, and hopefully the sign will be okay. So to satisfy our curiosity what is going on here, let's write W. After all, we should remember that whenever we are baffled by what something means, we are free, we have all the ingredients available to write it out explicitly in component fields. V is a superfield with so many terms. We can sit and act on it with D dagger, E, expand out everything and write the answer available for you to do. And you find that W A turns out to be lambda A. Okay, so there are two things. Yeah, sorry. Before I say that, the first thing we notice is that unlike V, WA is a chiral superfield. Unlike V. So the claim is that if I act with D dagger on WA, I get 0, and if I act with D, so this is D dagger, let's say B dot on WA, if I act with D of B on W dagger A dot, I likewise get 0. So W is chiral, W dagger is anti-chiral. How will we prove that? It's not absolutely simple. You'd have to take D daggers on this, so you have D dagger, D dagger, D dagger, D on B, and 3 D daggers can be shown to give you 0 for the purposes here. And one way to see that, it's not obvious again because D dagger is made up of a del by del theta and a theta dagger del mu. But by using this y variable, you can always take one of D or D dagger and shift it to be pure D by D theta. Okay. In other words, in the coordinates x theta theta dagger, D and D dagger are what I have given you, but in the coordinates y theta and theta dagger, one of these two simplifies, D or D dagger. It just becomes a pure D by D theta. So, in that case, of course, 3 of those will certainly give you 0. So, the proof in y theta dagger coordinates, which means we vary y theta and theta dagger independently, where y is that particular shift of x. Okay, one of D dagger simplifies to D theta or D theta dagger. How do we get the two choices? Of course, we choose either y or y dagger. We have two choices, two natural choices to shift x into y. With one choice, one of these becomes D by D theta. With the other choice, the other one becomes D by D theta dagger. Okay, you can just go into those coordinates, or again, I emphasize, you can just compute. By now, you're surely fond of. So once you looked at this W, you agreed to act with 3 D's on B. So now you'll be happy to act with the fourth one and expand out. You only have to do the 4 terms, 16 terms, work them all out, and you'll get 0. So it's easy to see in many different ways. So this is why we introduced W, because it's a chiral superfield. Now that it's chiral, of course what we'd like to do is to consider W of y and theta only, because it doesn't depend on theta dagger in the y theta dagger coordinates. And so we should have a short expansion for it. And let's see what that short expansion gives us. The important thing to realize is this is the first time we've come across a chiral superfield which has an index. And what index is this? It's a spinor index. This is the undotted spinor index, this is the dotted spinor index. Okay. So that means its first term is going to have a spinor index, so we're going to call it lambda A. In fact, not that we're going to call it, we find that it turns out to be lambda A. What was lambda? It appeared in B in the third order in theta. So obviously when we act with 3 derivatives, we'll pull out lambda. So it's the spinor part of the vector multiplet, but now it occurs as the first term. So last time somebody asked me if a superfield can also have an index, so here's an example. What are the other terms? We expect that the contents of this gauge multiplet have rearranged themselves nicely, and indeed they have. Finally, there's a term. index A on every term. So it's a little different from what we did before, because now we have to expand in a basis of thetas where one index remains free. All possible combinations of thetas which have one index free.
I'm confused.
Yes.
How is lambda A of y different than lambda A of x?
No. No, because a chiral superfield, when treated as a function of y, only depends on theta in addition, not theta dagger.
No, I'm saying the earlier lambda that we had was a spinner which depended on x.
Yeah, and so is this. I just have to expand this. So if I expand this in x, then I get lambda of x, but then I get some residual pieces here which depend on derivatives of lambda. So we've learned that superfields not only contain independent fields, but also those same independent fields may reappear elsewhere in some other component, and it always happens in a chiral superfield. Okay, because a chiral superfield doesn't really depend on only theta; it has a theta dagger dependence, but it's buried inside y. So there will be a term that I haven't written here, which will come from expanding these things with y expanded around x. Okay. But we see very nicely that d, which used to be the last term of v, has reappeared as the coefficient of theta. Okay, and the gauge field, which was the first term of v in the Zumino gauge, v was theta, sigma mu, theta dagger mu, and now occurred in the form of its curl of f mu nu. And this is great because it makes us suspect that WA itself is gauge invariant. So the advantage, so passing from V to W is like passing from A mu to F mu. Okay. In ordinary field theory, A mu is the fundamental field, F mu nu is a derivative of it, but it's gauge invariant. Here V is the fundamental field, W is a derivative of it, strangely 3 derivatives of it. Okay, so it's a not an independent fundamental field, but it's gauge invariant, unlike V. So the claim is when V goes to V plus I lambda minus lambda dagger, WA goes to WA minus a fourth D dagger D A lambda minus lambda dagger. And this thing, now let's look at this thing in more detail. Clearly D dagger DA of lambda dagger is 0. This on the second term, that's clear. Because this is an anti-chiral superfield gauge parameter. So if DA on it is 0. For the first term, a little more work is needed. You have D dagger DA on lambda. Now you need to do some work, which I'm going to leave to you, and you'll find that it's 0. But you have to be careful because you'll have a term when you commute D dagger through D, then it comes here, then it gives 0, but the anti-commutator of D dagger and D is a derivative del mu, and you have to consider that. Actually, it's easy. Actually, let me just tell you. So one term is the anti-commutator of these two, that's a del mu, but del mu goes through D dagger, so this D dagger comes in and kills. And after we've anti-commutated through, then this guy goes and kills directly. So it's actually very easy. Nothing to make a fuss about. Okay, so we see how the gauge invariant field strength. So WA and WA dagger play the role of gauge invariant field strength. Now you surely know that in non-abelian gauge theories, the field strength is not gauge invariant but just covariant. We'll be doing that next time. But for U1 theories, it's very, very simple. The gauge potential transforms by a shift involving derivative, and the gauge field strength is just absolutely U1 invariant. And here we have W's, which are invariant when V undergoes this shift. So they are the strict analog of F mu. Now in ordinary field theory, we know that the Lagrangian can be written directly in terms of only F mu. We got part of the way there, but we didn't finish because we have a Lagrangian that involves W, but it still involves V. Okay, this is very much like writing the action. This is what Gautam was asking. This is like F mu nu del mu nu roughly. Very roughly, be careful because this is not a first order super derivative of V, it's actually a third order super derivative of V. But what turns out is that by a little manipulation, we can rewrite this, dropping two of the integrals and only as an F term type of integral. So let me write down the answer for you. Let's write this here. In fact, we don't need to do a little manipulation, we just need to guess again that if we were starting from the beginning and trying to write a kinetic term involving only W, well, its canonical dimension is 3 by 2. Okay, so 2 W's has canonical dimension 3, and that's exactly the dimension needed to take care of d for x, d2 theta. And that's consistent because 2 W's is that if W is chiral, then 2 W's is chiral, no W dagger in it. And then I can only integrate it over d2 theta, not d2 theta dagger. So this of WA plus its complex conjugate is a candidate kinetic term, and my claim is that it occurs with coefficient plus 1/4. So this is an identity. I am saying that this written entirely in terms of W is the same as this written in terms of W and V, which is the same as the thing written entirely in terms of V. These are all different ways of writing it. Okay? And again, if you don't believe my general arguments, you just can take this thing, write out the expansion of W, which is here, and evaluate all the theta integrals, and you'll get half d squared minus 1 for F mu nu plus I by 2. Okay, so experimentally, it does agree with the kinetic term we wrote down previously, and this is one way to derive an identity. It can also be done directly in superspace. One-fourth integral d2 theta WA plus C is equal to 1/8 integral d2 theta dagger d dagger b. And therefore you see that this is a very pretty thing. The gauge potential, which is really V, is a vector superfield. Therefore, this is a d for theta integral. But the field strength associated with it is a chiral superfield. Therefore, this is a d2 theta integral plus its complex conjugate. So, in this case, we see that the gauge kinetic term and its super partners can be written either as an F term or as a T term, whichever we prefer. Each has its own advantages. But generally, this is more common. F terms are always easier because there are less theta integrals to do. Okay? Very good. So there's a little more to do, but if I put on a little speed, I can do it in 10 minutes. Are there any questions? Okay. The last thing that remains for an abelian gauge theory is to work out interactions. We've only got the analog of, we've only got the kinetic terms. By the way, I suppose it's obvious and doesn't need to be stressed, but notice here that there is no sign of a mass term for lambda. Lambda is the fermion. It might have wanted to have a mass, but it's the super partner of the gauge field, and the gauge field can't have a mass without breaking gauge invariance. And the way we find out that over here is that there is no gauge invariant term which will simultaneously give me this as well as the fermion with the mass. In fact, there is no supersymmetric invariant term and gauge invariant term which can do that. And that's an example of a very general fact that the mass of all fields in a given supermultiplet has to be the same. Because supersymmetry transformation takes you from one field to the other. Okay? And that commutes, if you like, with the zero component of the Hamiltonian, which measures the mass. Now, we won't ever have to introduce any more kinds of fields. We've already introduced all the fields that we'll be using. So things become very easy now. We are going to consider now a system involving one or more vector multiplets. I think actually only one vector multiplet for the moment. I'll generalize it later. And a bunch of fields phi I and phi I dagger, which are chiral multiplets, with I going from 1 to some n, is the number of flavors, if you like, is the number of fields. Okay, this is a simple class of models that we'd like to discuss. Now these are independent chiral superfields. I'm bringing them back for the first time today. These have nothing to do with gauge transformation parameters. Because I was focusing on V for the whole lecture, and now I'm trying to look at a coupled system of V and phi's. Because these are matter fields, these are gauge fields, and they're supersymmetric properties. Okay. Now, ordinary matter fields transform under U1 by a phase, extremely well known. So, the scalar component of these things will go, let me establish my conventions here, e to the I g ti beta of x, while this is copied from the DGR book. G is the coupling constant, sort of an arbitrary definition for a U1 theory. These are the charges in units of G of the individual fields phi. These are not any matrices or anything now, these are just some charges. Okay. In the case which we'll be applying it to, for example, G will be chosen to be Q, which is the electric charge of the electron, and then T for the electron will be +1, because the electron has a charge plus Q, where Q is its own electric charge, which is a negative. These are conventions. And then T will be -1 for the positron. Okay. And here whatever T is for phi, it will obviously be minus of that for phi star by complex conjugating this equation. And beta of x is the arbitrary gauge parameter. So, G coupling, G1 coupling, Ti charge in units of coupling, and beta x gauge parameter. And now we need to generalize this transformation to superfields. Okay. So we need to ask, what does phi I go to? It's extremely simple to answer. It's very uniquely fixed, because capital phi has small phi as its lowest component. Okay, and we know that the gauge parameter in superfields is this capital lambda and lambda dagger. Okay, and somewhere buried in that capital lambda is a parameter alpha. In fact, the first component of that lambda is a parameter alpha, which is the gauge parameter, except that it differs from this beta by a factor of -2. You remember that the gauge transformation was -2 del mu of im alpha, but we'd like to call it plus del mu of beta in this language. So we just identify the two, and we are immediately led to the statement that phi I goes to e to the -2i g di, the superfield lambda of y and theta, phi I of y and theta. Why are we led to this? Two reasons. First of all, phi is a chiral superfield. So after a gauge transformation, it has to remain a chiral superfield. That will happen if the gauge transformation is parameterized by a chiral superfield. Okay? And there was such a chiral superfield occurring in the gauge transformation of V, because we went to V plus I lambda minus lambda dagger. So we must pick that lambda and not lambda dagger and use it to define the gauge transformation of phi. So it transforms by a phase, but it's a superfield valued phase. A phase which is an e to the I superfield. Okay, that's one observation. The second observation is that if I restrict phi to its lowest component, this phi to its lowest component and this lambda to its lowest component, and take that component to be imaginary, then I get the same as this with minus 2 alpha identified with beta. So that works. Okay. And the third thing is, of course, that so that's it. The fact that this is a chiral superfield after this transformation, and that it reduces to the gauge transformation on the scalar component uniquely defines it. For the anti-chiral superfield, we just dagger everything inside, and we get e to the plus 2i g t I lambda dagger of y dagger and theta dagger phi dagger I of y dagger. Okay. Now the next step would be to somehow couple these fields to the gauge field to find a gauge invariant coupling, analogous to minimal coupling for an ordinary scalar field, charge scalar field coupled to a gauge field. We know that if we took this field in ordinary field theory and wrote del mu phi star del mu phi, that would not be gauge invariant because it would pick up derivatives of beta, and we know that del mu has to be replaced by del mu minus I a mu. So a mu has to come in. The analogous statement here is that phi dagger I, which is the kinetic term for these phi fields, is not gauge invariant. Can you see why? Because under gauge transformation, it goes to e to the 2i g t I lambda dagger minus lambda phi I dagger phi I. This being the piece that acts on phi, and this being the piece that acts on phi dagger. This thing is not going to be 1 unless lambda dagger is equal to lambda, but that's impossible because lambda is a chiral superfield. Okay, and we should be happy about this because it would be very weird if the kinetic term of this chiral superfield were gauge invariant without putting in the gauge field. It can't reduce to ordinary field theory as we know it. So the gauge field better do something, but there are not very many things it can do. Since V shifts by the piece proportional to lambda minus lambda dagger, we are obliged to put an exponential coupling to V. And that is that the kinetic term is replaced by, and this is the analog of minimal coupling, phi I dagger e to the 2 g e to the 2 j t I v phi. Writing this exponential in the middle is not strictly necessary. These are all things that commute with each other. There are no matrices here. We don't deal in gauge theory. I can put it anywhere I like. The important thing is phi transforms with this phase, phi dagger transforms with that phase, and V transforms by a shift which produces a phase exactly equal and opposite to that. And this thing is therefore gauge invariant. And I don't have to write for you again what are the transformations under which it is invariant. Phi going by a phase, phi dagger going by a dagger of that, and V going by a shift. There are two very important nice things to note, because this might look very alarming. For example, we are not used to having exponentials in ordinary field theory. Standard model has no exponential couplings. You might think exponentials violate renormalizability because we can't have more than dimension 4 couplings in ordinary space. But remember what was the canonical dimension of V was 0. Okay, and actually in a natural way. So thankfully that's consistent with this. But even more interesting, in Zumino gauge, V starts with theta theta dagger. Therefore, the third power of V is 0. V cube is 0 in Zumino gauge. It's not 0 in any other gauge. That's because that gauge removes the first few components so that it starts with theta theta dagger. So 2 powers is okay, 3 powers is not. Okay, but that's it because V is linear in the gauge field mu, and we are seeing that there is never going to be a third power of that gauge field in the action, which is in fact what is true in the standard model. The first power of gauge field will be the term like A mu phi star del mu phi, or A mu psi star gamma mu psi, and we know that with scalars there is also another term A mu phi star phi, which is in fact the term that gives a mass to the gauge field by in the root standard model. So second order in A mu is definitely there, but the third order isn't there, and therefore we see that things have a very good chance of coming out right. So I better stop now, also because I think this tape may run out. So what I'll do next time is to come. Okay, so anyway, I think I can write the final conclusion here. Next time I'll just write for you the component field expansion. You can also do it yourselves. So at the end of the day, we have the full Lagrangian. The full action is integral d2 theta dagger phi I dagger e to the 2 g d I v phi I. There is a sum over I first, so that is species, plus the gauge kinetic terms WA plus CC, known as the 1/4, and finally, since these scalar fields are part of a scalar field theory on their own, they are entitled to have a superpotential. So there is a term involving W of all the phi I, and its complex conjugate. This is the flow theory. Okay. It's not strictly the most general, because you would have noticed that in this term I could have put in a scalar potential instead of this phi dagger phi structure. Okay, in principle, but that's certainly going to lead to non-renormalizable interactions, because that leads to a nonlinear sigma model which is non-polynomial in finite 4 dimensions, and that we can consider an effective field theory, but we certainly can't consider it in the standard model or MSSM, because those are fundamental and not effective. They're supposed to work as fundamental theories, namely they're supposed to be renormalizable. So then this is the most general action involving gauge invariant and supersymmetric action involving scalar fields coupled to a U1 gauge. Actually, there's even one exception to that statement, but I'll do it next time. Okay, I think it can be set off. G y squared plus G2 squared square root times V. So the mass of the Z differs from the mass of this by an extra Gy, and we see that it's strictly more massive than that. So it's nice that we have really not done anything that can be called phenomenology, but we've already seen a true experimental fact coming out. Okay, we are still building up to the phenomenology. Now to close, I'll just rewrite this matrix in a nice way. So let's pick our favorite Nobel laureate, let's say Weinberg, and let's call G2 over this thing as cos of theta Weinberg. And then this is an appropriate way to parameterize any orthogonal 2x2 matrix, and theta W is called the Weinberg angle. I'm trying to remember who it was who claims that it stands for Glashaw's weak angle. Salam, maybe. Anyway, good. I think I got it right. Cos theta should be G2 over the root, and sin theta should be Gy over the root. Okay, so I hope that this fixes physical ideas quite well. Gy and G2 are our most important input parameters. They were the coupling constants of the hypercharge and the SU2 gauge group. And now we see that depending on some kind of angle in Gy G2 space, we have a single angle, Weinberg angle, which tells me the amount of mixing between SU2 and U1. Has the tape run out?
Almost 3 minutes.
Very good. I also almost run out. Good. I think from this point, so let me just write the last formula because it's pretty. So Z mu is cos theta W times W3 minus sin theta W times V mu, and A mu is sin theta W3. Okay. And A mu is massless. And here there is absolutely no ambiguity in this theory because it's massless and it's the only massless gauge field. It has to be identified with the photon. Okay. So I'll stop here. And next time, I think we've made good progress. So I think we can pretty much complete the standard model next time, which is what I've connected. So next time we'll complete this by talking about electric charge assignments, and we'll fix up all the hypercharges for everybody from experiment. And then we'll talk about mixing, mass matrix and mixing, and then we'll go on